Hello, engineers. Welcome you to lecture number 5. Of course, this is a supplementary of lecture 4 and 5. There was a part in lecture 4 which I decided to skip. That was something to talk about reduction of a simple distribution load. But after we went through lecture 4 and lecture 5, I thought like this is the right time where we can now discuss on how we can reduce a simple distributed load. The main objectives are: 1. To indicate how to reduce a simple distributed loading to a resultant force acting at a specified location. And the second objective is to calculate and resolve couples force resultants, and of course using equilibrium equations for rigid bodies with distributed loading. You can remember that equilibrium of rigid bodies, this was covered in chapter 5, and the moments and couples were covered in chapter 4. Here I'm just showing you how or what type of loads are those that we might call distributed loading. This you can see, this is of course, this is a human being that you can see seated on a chair, of course, in a vehicle. That is a headrest. Now the load that has been distributed is supposed to be equal for this rest to be in equilibrium, or rather for it not to rotate. So the force that the human being is applying is equivalent to what the force or the reaction that the headrest is also applying. So this is what we are going to look at in this lecture. Sometimes a body may be subjected to a loading that is distributed over its surface. For an example, the pressure of the wind on the face of a solid wall, the pressure of water within a tank, or the weight of sand on the floor of a storage container. These are all distributed. As the example that I've given you here, you can just see that this is just soils, right? Coming from a flower pot. Wherever is resting, there is some force, there is some weight that is exerted to the supporter. In this case, it happens to be the foundation or the floor, whatever you are going to put that. So, looking at the surface area, you would realize that at each and every point there are some loads that are coming from this sample. What we are going to do is to reduce these number of these parallel forces weights to be equivalent to 1. In short, what is a distributed load? There are examples here. You can see this is a dam wall. Here there is water. The other side there is automatically, where there is water, that side, the other side, you're going to find gravel, or let me just say soils, which are also protecting the dam wall from collapsing. Without the soils, this body would collapse. without the embankment itself, the source, this water would make the dam wall to collapse. So what is happening here is the water that is being stored in this reservoir dam, it is exerting some forces towards the dam wall. Now, to make sure that this does not collapse, we also have the embankment, the soils, which are also exerting some forces against the dam wall to collapse. This one is just showing us the reality where you're going to see a beam, then you have got some supports there. Maybe the length can be 5 meters. This is how the load is being distributed. At the end, when calculating, when designing, we try to reduce that into a point load. This also applies to this model, also applies to that model. Analyzing distributed loads. A distributed load can be calculated with a concentrated load applied at a specified point along the bar. This is a distributed load. It looks like a triangle. You can reduce this just to be a point load. This also applies for this member. This is not a rectangle. This line is not a straight line. We have to reduce this distributed load to a point load. The most common types of distributed loading encountered in engineering processes can be presented along a single axis. As an example, consider the beam or plate in figure A that has a constant width, which is B, subjected to a pressure loading that varies along the x-axis. This loading can be described by the function of P is equals to P bracket X. And of course, this is pressure, it will be Newton per square meters. It contains only one variable, which is X. And for this reason, we can also represent it as a coplanar distributed load, which happens to be this. You have your length, you have your X, you have your weight moving from the left to the right, reducing. But these parallel forces, they are changing, starting from 0 to L. This can as well be reduced to be one single point load at a specific distance or location. Of course, to do this, you only need to multiply the function that is a px times b. Using this method, we can replace this coplanar parallel force system with a single equivalent resultant force if are acting at a specific location, as I've already alluded. This, if this was a triangle, it was going to be easy for us to get a rectangle. It's going to be easy for us to get the resultant force, because these are forces parallel in the z-axis. That is, if this is the z-axis. If that is the z-axis, in this case it's a W, which simply means the weight. So these are parallel forces, number of them, but it will be very difficult for you to count how many are they. So there are two different types of scenarios. The first scenario is where you have been given a triangle, you have been given a rectangle. The second one is where you have been given a circular, or where there is a curve. So if you have given a rectangle, a triangle, the area that has been covered by that specific weight or load, that is your resultant force. In this case, we had a 10 kilonewton per meter, which starts from after 1 meter, 3 meters length. So the area will be 10, which is that, multiplied times 3. Then you get the 3 kilonewton. That is going to be your resultant. In terms of the location, this is simple algebra. The center of a rectangle will be 3 divided by 2, which is 1.5. So even the equation itself is going to show you to get the location of x from 0, it will be x, the distance from 0 to where the distributed load is starting, plus half the breadth of that rectangle. In this case, which happens to be 1 meter, half of 3 meter, we're going to get 2.5. This is where we find the location of that resultant force. For a triangle, we all know about the area of a triangle, that is half BH, the breadth and the height, right? So in this case, I've got a situation where we have got a 5 kilonewton per meter, starting from 0, we get the area, which is going to be 10 kilonewton per meter. The location, we use the same equation, which is x0 plus 1 over 3. Where is that 1 over 3 coming from? Always a triangle, for you to get the center of gravity is 1 over 3 of the length from the larger end. So if you can remember that, then you apply 1 over 3b, then you're going to get a 4 over 3. That is where you're going to apply. That will be your location for the resultant force. Then we go to the integration method. The magnitude of FR, which is the resultant force, is equivalent to the sum of all the forces in the system. This one all of us will know. The resultant is always the addition of all forces in that specific direction. In this case, integration must be used since there is an infinite number of parallel forces, dF, of different magnitude acting on the beam. There are a number of parallel forces acting on the beam of different magnitude. If it was a rectangle, if it was a triangle, it was going to be easier, simply because we know the shape. At the end, it will be the maximum, at the end, it will be minimum. And at each and every point, we can easily calculate the area. But in this case, we need to integrate for us to get the area. So, since dF is acting on an element of length dx, and Wx as a force per unit length, which happens to be the force that is supposed to be, that is applying to the beam from 0 to L. In other words, the magnitude of this force is determined from the colored differential area dA under the loading curve. As you can see, the area of this curve is going to give you the FR, the resultant force. Therefore, for the entire length L, summation of forces would give us integration of Wx dx. In other words, we are just integrating the area of that graph. The magnitude of the resultant force is given by the integral of a curve defining the force Wx. In this case, we have got this example where we have got the force itself is x to the power half. How do we calculate the magnitude? We are just going to integrate starting from 0 to 5. And the equation for our curve is x to the power half. You do your integration, you are going to find your FR, your resultant force is 7.45 kilonewton. To determine the location of the resultant force, the location x of the line of action of the resultant force can be determined by equating the moments of the force resultant and the parallel force distribution about point O, the y-axis. Since the df, the differentiation of f, produces a moment of x df, which is x wx dx about O, figure 4.1, that is B, this one. Then for the entire length, you are going to find summation of moments. It will be a negative x will be equals to the integration. That is the length, the x, and that is the force. When you solve for x, you are going to find x being the location to be the integration of the force itself, which is the area over, the integration of the volume divided by the area. If you remember this equation, we are just doing some integrations, getting the area of that curve, which happens to be this curve. So for us to get the length, x is the volume divided by the area, which happens to be the differentiation of the area over the volume over the area. This coordinate x locates the geometric center of centroid of the area under the distributed loading. In other words, the resultant force has a line of action which passes through the centroid C of the area under the loading diagram. Detailed treatment of the integration techniques for finding the location of the centroid for areas will be discussed in other coming lectures. I think after lecture lecture 12, that's when we start looking at the centroid, center of gravity, and so on. This is just an example. The location of the resultant force is given by the centroid as given. This is just an example where we have the curve is given by, we do our integration to find the location. This is the volume and this is the area. This, remember, we find the area as the force itself, which is going to give us 3 meters. That's where you're going to apply, where you're going to find the FR as the resultant force. Another example. For a vertical bar, determine the resultant force and its location. We are going to apply the same principles. The first thing that we do some integration, getting the area of that curve. It is moving from 0 to 5. This case, it is in the y-axis. We find the area, it will be 41.7, which happens to be the FR, the resultant force. Then we do the same with the location. The location, it will be now we calculate the volume over the area, which is 41.7. We do the same integration here. This is going to give us the volume, this is going to give us the area. Then we'll find the position where our FR is being applied. Another example, determine the length B of the triangular load and its position A on the beam such that the equivalent resultant force is 0 and the resultant couple moment is 8 kN/meter clockwise. We all know that we agreed the clockwise moment is negative unless otherwise. When you want to say it's positive, make it positive and be constant. So in this case, what do we have? We have the load 6 kN and we have the other load facing the other side, which is 2 kN/meter. This one is a triangle, the other one is a rectangle. We don't know the length, that is B plus A, and we don't know the length, the other length for the triangle, which is B. The only thing that we know is just the height for a triangle, which is 6, and also for a rectangle, which is 2. From there, automatically we have ideas on how we are going to calculate this. We have already been told that the moment is 8 kN clockwise. That you simply mean this thing is supposed to be falling in this manner, right? So you put your force there. Now this is a fixed joint, which simply means you are supposed to have another member facing this direction in the X and the other one in the Y. If the moment is going like that, you can assume you're forcing the X to be facing the left side and the forcing the Y to be facing up. When you get the negative, then it shows that your assumptions were wrong. If you find positive, then your assumptions are correct. So using the same principles, you start with summation of forces in the Y. What do you have? You have one force there and you have got another force there. How do you get that? You remember those equations about 1/3? and a rectangle is 1 over 2. These are the equations that you're going to have there. Then you have that. Summing the moment about A with the requirement that the couple moment is equals to A, which is going to give you that. Summation of moments is negative 8. As you agreed clockwise, is negative. Will be equals to 2A plus B brackets 4 minus 1A plus B. This 2A plus B is the distance. Is the force that we have as 2A plus B. Multiply times the distance, which is 4 minus 1 over 2A plus B. Minus, this guy is going the clockwise manner. So it's going to be 1 over 2 6B times, when you solve these equations, you are going to find 1.26, and at the same time the B will be 2.53. If you remember, I mentioned about point A, you can, because that is a fixed joint, that will simply mean you are going to have a moment, you are going to have a force in the X and a force in the Y. But even if you add them, they won't work, simply because we are getting the moment about point A. So even if we add those moments, they don't add anything. They will still be 0. Another question. The distributed load acts on the shaft as shown. Determine the magnitude of the equivalent resultant force and specify its location, measured from point A. Here is a matter of integration. We have the equation for the curve. What we do, we first find the area under this curve. Once we find the area by using this equation, once we find the area under this curve, that will be our FR. Once we have our area, the next thing is now to find the volume. How do we get the volume? It's by integrating the area times the distance. The distance in this case, which happens to be the X. Once we find that, we divide those two, the volume over the area, then we get the location where our FR, our resultant force, will be. So as you can see, this is just the integration of getting the area, which ends to be 73 pounds. Moving from -1, because where we already had a W, so it was a -1, up to a 4. Even if you move this guy, you put him there, you have 0 to 5, you still get the same thing. You still get it 73.3 pounds. Then the next thing is to find the volume. The volume is the area that you got, which is this, the equation itself, times the distance. In that case is X, which is moving from 0 to L, which is, in this case, which is going to be B. You do your integration, you're going to find 89.116. Then to find the position where your resultant force is, take note that here you use the -1. So your 0 starts from where W is. So where your 1.22 is, it starts from where your W is. In this case, it is 2.22, which happens to be where that force was applied. Another example. Replace the loading by an equivalent resultant force and specify its location on the beam measured from point A. This is a rectangle, at the same time there is a triangle. So how to solve this problem? You can easily draw a line by making this is a triangle, 2 kilonewton per meter, and the remaining one is 3 kilo per meter. Right? So the first thing, you know how to get the FR for the rectangle, which will be the 2 times the 6. Right? Once you get that, the location will be the 6 divided by 2. Then we go to the triangle. The triangle, it will be 3BH. Right? The 3 automatically is our B. Then our H is a 6, so which is half BH. Then where is the location? The location is 1/3 starting from the larger force. So in this case, this is how they have solved this, where you find the two forces. The other one is 2 times 6, the other one is 1/2, 3 times 6. Right? But how are you going to find where the FR is? This is very simple. You can say, find a moment about A. You know the first force, you know the second force, and the third force, that is the distance that you are looking for, multiply times the FR, of which the FR we know, which happens to be 21. The only thing that we don't know is the distance. Solving for D, you are going to find is 3.43. Another question. Replace the distributed loading by an equivalent resultant force and display its location on the beam measured from point A, measured from the pin at A. This is the same scenario. You come out with, to make a rectangle which is going to be 2 kilonewton per meter, and the remaining one will also be that, will also be 2 kilonewton per meter. So you do the same. For a rectangle, is the area is equals to BH, 2 times 6. Then for a triangle, it is half BH, which is 2 times 3. Then you are going to have one load here and another load here. Once we have these two, force 1 and force 2, Then you say summation of forces in the y will be equals to F1 plus F, right? You will be able to get your Fr, sorry, this is R, the resultant force. Once we have that, then we find the moment about A to find the location of that specific point. This question is just the same like the previous one. So, summation of forces in the y. You have that, but before you leave that, you get to that they had to split those. There's a 2 and a 2. So you get that, and you're going to have those two forces. Once you have those two forces, summation of forces in the y, which is you're going to have that Fr should be equals to 2 times 6 minus half. Then you're going to find that. The location, we do the same. We get a moment about A. Another question. Determine the reaction at the supports. Now, the reaction that you are looking for, if you remember from lecture 5, this is Aurora, you are only going to have this scan is going to allow the translation in the horizontal, but it won't allow in the vertical. So you're going to have one there. This is a pin. Here you're going to have both. It doesn't allow in the vertical translation and in the horizontal translation. So you're going to have two, Fx and Fy. So from here you do the same. You create, that will be, if that is 600, that is 900, that will be, this is 600, and that will be 300. You have just created that, which is 300, right? And that is of course, that will be 3 meter. That of course is in Newton per meter. And you have another rectangle which is 3, and that is 600 Newton per meter. We are going to have one force. Sorry, this is supposed to be 6. We are going to have a force here, F1, and another one here, F2. F1 will be equals to the 600 times 6, and the F2 would be equals to half times 300 times 3. Once I have a force here, another force here as F1, whatever, F2, then summation of forces in the y. These F1, I would say negative, F1 negative, F2, the other one's going up plus F, this one will be Fy3 and Fy4. Fy3 plus Fy4. this is supposed to be equals to 0. That's how we are going to get the fy3 and fy4. This is how you solve like what I just from explaining. You're going to have unknown there, an unknown there, and a by. But the by, unfortunately, there is no any other component. You find bx to be 0. It is, in short, it is a redundant as shown there. This is how simple this thing. I'm sure this is supposed to be the last example. The bulkhead AD is subjected to both water and so backfill pressures. Assuming AD is pinned, AD is pinned, AD is pinned to the ground at A. Determine the horizontal and the vertical reactions and also required tension in the ground anchor piece necessary for equilibrium. You remember about equilibrium, summation of forces should be equals to 0. Summation of moments should be equals to 0. We know that. And the bulkhead has a mass of 800, meaning this, it is 800 kg. So, of course, from this, you are going to have the load, which is 800 times 9.82, right? Then at the same time, we've got a force F1. Then at the same time, we're going to have another force here, and here we're going to have another force there. And here, this is a pin. We're going to have another force there and another force there. Then we just play around with summation of forces in the x should be equals to 0. Summation of forces in the y should be equals to 0. As from what I was just explaining, you have a force there, you have another force there, you have another force here. I've got twisted. There's a pin here, right? Summation of moments about O, which happens to be this point, it's supposed to be equals to 0. So we have got how many forces? 1, 2, 3, which happens to be the 107. How do you get the 107? By calculating the half, the 310 times the 6.5. You get that. Now we look at the direction of this. This is going counterclockwise. So this is positive. When you look at the F is going the other side, is going clockwise, that is negative. When you look at the 236, this there's a triangle there, half, the 18 times 4 is behaving in the same manner clockwise, which also is going to be negative. This is what you're going to get there. And an equilibrium is only supposed to give you 0. You get your 318. Then you come to summation of forces in the x. Summation of forces in the x, you have, depending on which one I've chosen to be the x. In this case, this is the horizontal is the x, which is the F1. The F1 in this case is 3111, which is positive. The 1007 is going the opposite, is negative. The 236 is going in same line with F, which is 311, positive. Then the unknown is AX, which is this. Using your simple mathematics, you'll be able to get. Then you do the same summation of forces in the Y. you are done. These are the homework exercises that you're supposed to go through. Take note that these questions are coming from lecture 4 and lecture 5. As earlier I mentioned that this component was supposed to be done in lecture 4, but I decided not to put it there. This is the right time where once you understand something, you can apply it on problems that you'd have in lecture 4, and also problems that you have in lecture 5. Please find time, go through. This is not even difficult. This is very easier because we are just trying to apply the tools that we started with, starting from lecture 1, lecture 2, lecture 3. We are just applying the tools that we already have. So find time to go through. When you are done with this, there are a number of questions in different books. Go through. This will help you. Once you try to practice, you are becoming better. Whichever question comes, the thinking becomes open. That prison I normally talk about, you're supposed to have a thought of freedom. When you look at something, you're not supposed to be limited. You're supposed to think. That's how all those ideas will be coming. Otherwise, life, it has never been simple, and it will never be. That's the reason why we are equipping you with this type of tools and problems. Once you solve these problems, I'm sure all the problems that you encounter in future, it won't be a matter of like something that will challenge you. Hope what I've explained, you got one or two. Have a good day. I'm done.